Hello, my name is Kreuger, and I'll just jump right in, talk about human behavior modeling. So today I'm just going to go over a little bit of the motivation for human behavior modeling, the way it's typically done. I'll kind of scope out a little bit of maybe some of the ways that the modeling I do in public health is maybe a little bit different than some of the stuff that is maybe presented here. And then I'll go through the modeling specifically that we did and look at the behavioral model that kind of came out as a result of that work. So the first thing I'd like to talk about is that whenever we're building a model that includes humans in it, there is at least an implicit model of human behavior. And in a lot of cases, we need to be explicit about that model. And then when we need to be explicit about that model, we often rely on a set of very simplifying assumptions, often so that our equations work or so that we can understand it. And these are some of the assumptions that we typically make. So we typically assume that the agents or the people in our model, they have perfect knowledge of everything they need to be able to decide. We assume that they have effectively infinite computational ability. And we also assume that their objective function is often quite simple. It's usually, maximizing my costs or some sort of other simple objective function. But humans actually have very complex, the decision landscape for humans is very different. So first of all, humans, we don't have perfect knowledge. This is widely recognized that we don't have perfect knowledge. We also have limited computational ability. So this requires us to use complex sets of heuristics to be able to make decisions. And finally, the objective functions that we're using are much more complex. They are often conflicting, and many of them at the same time. It's not just a question of, maximizing your economic output, but it might be based on social relationships or based on patterns of habit or addiction or all sorts of complexity that comes in there. And so the goal of my research and the goal of this talk is to start looking at ways where we can move from the simplifying assumption that we know is false to something that's a little bit more realistic. So the goal here is to come up with a way of comparing different behavioral frameworks and then decide on one that will be used in a policy model. So I'm just going to talk a little bit about the modeling space that I'm operating in. This diagram, it's fine that you can't really understand it. It's a causal loop diagram. So for those of us who know what that is, this is looking at the causes associated with obesity. I just pulled this from the web. It's just an example. But this is an example of the type of systems that we're working in public health. So we're dealing with a lot of feedback loops, and this was mentioned a little bit earlier in another talk. Feedback loops have the tendency to dampen or to magnify external causes, so policy changes that we might put in place. There's also delays in causation, so it might very well be the case that a policy you put in, like a tobacco control policy or a policy on sugar-sweetened beverages or something, it might need to be in place for several years to be able to observe output. So we want to be able to know that that's the case. And finally, there's a lot of other examples of nonlinear relationship that's happening in these complex adaptive systems. Compounding this is the fact that we're dealing with social systems. So the data that we have is often missing. We often don't have data that describes, the thinking about how somebody's making a decision. We don't have the data. So, and even when we do have data, it's often very noisy. It's captured under different sets of assumptions. Different organizations are capturing it. And often the data we're capturing it as a proxy for something else that's more fundamental. So there's all sorts of reasons why the data that we have is often very suspect. This leads to unclear causal relationships. So if we don't understand the causes, then it can be very difficult beyond using statistics to understand what's going to happen into the future. And human behavior is exceptionally unpredictable. And finally, the policy environment is often very decentralized. You have many different decision makers, agencies, companies that are responsible for making policy that's going to be within the system. And so a perfect model would actually include the behavior of all the policymakers as well. And so for this reason, the modeling that I focus on, the modeling that we focus on, and a lot of the modeling in public health, population health, public policy, is less about optimization and prediction and more about generating useful insight and explanations for what might be happening. So this is just sort of a framing to sort of see the kind of modeling that I'm doing. So the example that I'm talking about here is tobacco control. Tobacco is a leading cause of preventable mortality, and so various organizations are trying to figure out ways of reducing tobacco usage in a population. lots of interventions have been attempted and studied in the literature and research and across the world. Excise taxes is a common one, age restrictions, social media campaigns, advertising limitations, all sorts of things. We're focusing in this work on an excise tax, so we want to look at what types of behavior are going to result from having an excise tax. And the types of behavior that have been documented in literature are so-called price minimizing behaviors. And so this is where people have behaviors that sort of respond to a pricing change to minimize the increase, the effect of an increase in pricing change. So they do this through coupons, through changing from cartons to packs or packs to cartons, through switching between different pricing tiers, maybe going from tobacco cigarettes to e-cigarettes. There's all sorts of behaviors that people can do in order to kind of counter the effect of an excise tax, of a policy change that we put in place. So we want to understand what types of price minimizing behaviors people will engage in. So the model itself, TPMS, Tobacco Price Minimizing Strategy Model, we built it using data from the Minneapolis metropolitan area. So we have an urban core, there's a ring, that's like a suburban ring, and then on the outside, there's a rural area. The agents in our model, they're people. They have a work schedule. They go between work and home according to the schedule. They have social network connections. They also have peers that might not be in their social network, but they're at work. They have various demographic information. And then the choice landscape for tobacco is the tobacco retailers. Again, we have tobacco retailers in each of the areas of the city. They have different products. They have different prices. They can have sales on different products at certain times. And we can have taxes on some segments of that product and not on other segments. So we can have a pre-tax environment. We can run the model. We can get people buying and smoking and quitting smoking and initiating and relapsing and all that stuff. And then we can initiate a tax at different levels, and we can see how the agents respond to this tax. And we can look at some of the unintended consequences that happen as a result. So again, the goal of this particular model is to study behavioral frameworks. And so you can see on the left, there is just sort of a simple representation of the agent network. So we have agent networks. Again, they're occupying a social space, and they're occupying a physical space, so they're at work or not at work. And then within the agent, we have various state charts and parameters and variables. So it's an agent-based model here. And then we have this framework agent. You maybe can't see it says framework agent, but the little red agent inside the agent is a framework agent. And so the idea here is that we would take the behavior that we care about and bundle it up into that framework agent. And so you can see there's 3 different behavioral frameworks that are being used there. You can have a statistical framework. A common approach is one based on Markov chains. You can have a complex feedback-rich system dynamics model in there. Whatever you want to put in there, you can put in there. And the key thing, one of the reasons why we're using AnyLogic is because we can leverage some of the computer science tools from Java. So in this case, we're using a Java interface to basically specify that the behavior of that framework, the agent only needs to care about the inputs, outputs. It doesn't need to care about how the framework is calculating its numbers, it's coming up with the values. So at any point, the agent can go, what's my probability of this happening? And then we just query the agent, the decision, the framework agent, and it gives that a number. So the idea is we want to be able to run the model, changing nothing except the behavioral framework, so that we can explore what different assumptions about how people make decisions how's that going to change the output from our model. So the basic idea is we use some considerations, which I'll talk about, some considerations for the behavioral framework. We come up with a number of different behavioral frameworks. In this work, we probably had 15 or 20 different behavioral frameworks that some came from literature and whatever. We generate a bunch of simulated output. We have a fair amount of statistical, empirical data from the Minneapolis area. And then we run comparisons, and we can compare them against it's not just one number comparison. We can do multidimensional comparison. And then from that, there's a feedback there where we basically make changes to the behavioral framework, or we adopt a new behavioral framework, or we throw out one. And in the end, we've chosen an optimal framework that will be used for the policy model. So for the first of 4 considerations that I found when we're building this and doing modeling in human behavior, the first is to consider scope. It's a very important component, because this is not a model that's about optimization. So there's always going to be things that are not included in the model. There's a lot of latent dynamics and characteristics that are taking place for which we don't have data. So we really want to avoid the kitchen sink model, right? We don't want to have everything in the model. So we want to scope our question as clearly and as effectively as possible. The scope might change over your project, but it's important to consider it. So the scope that we have for this project is that we've broken important behavior into two pieces. So on the one hand, we have smoking behavior. We know that this is not driven by, it's not a rational behavior. There's rational pieces maybe, but overall it's driven by addiction, among other things. So we wanted to be able to have a behavioral framework that included non-rationality there. And then the purchasing behavior, we decided to leverage a standard econometric tool called the discrete choice experiment. And that basically assumes that it's a statistical test where we do a survey and we get it assumes that people are boundedly rational. And so then we take these two things together, and there is an interaction because you can't smoke if you don't have cigarettes. And if you've got 100 cigarettes, you're probably not going to buy. So there is some interaction, but we're able to scope it effectively. The second consideration is the nature of feedback. Humans are very feedback-oriented. Our heuristics are very feedback-oriented, so we want to be able to have behavioral frameworks that accommodate for feedback. Not everyone does, but we want to be able to include some that do. So this is just a couple examples of the feedback that we looked at. So for example, the more you smoke, the greater your level of addiction, the greater your desire to smoke, the more you smoke. So there's this feedback cycle that's taking place there. And on the other side, it's sort of at the social level. As you increase the number of people who smoke, you increase the social acceptability of smoking, thereby increasing the number of people who smoke again. So there's a whole number of different feedbacks that we wanted to make sure were included in some of our frameworks so that we could compare and test them. The next consideration is the importance of perception. So if you look into the literature about how people make decisions, there's often a difference between people's perception and the reality. And so this is just one example of a key perception that we wanted to test. And so the idea here is, again, within the context of smoking, and for a smoker, the more my friends smoke relative to me, the less extreme I perceive my smoking, the more comfortable I am smoking more, right? So there's some behavioral frameworks that accommodate this level of perception, and that's just a key thing whenever we're dealing with human behavior modeling. And the last piece is we want to make sure that the behavioral frameworks have some degree of external validity. I mean, it can be very difficult when there's a lot of latent characteristics to make sure that you've got external validity, but you want to be able to verify it as much as you can. And so the top one, the standard discrete choice experiment technique, that's been validated in the econometric literature, so we use that one. The bottom one is an example of one of our frameworks. It was developed, it's a mathematical model, it's a sequence of differential equations used within a lab setting to look at mice and cocaine use. And then it was sort of ported to something more realistic for humans and tobacco. That was research done by other researchers, and so then we used that model within our framework. But it's important to consider this level of external validity. So then when we run the model, again, about 20 different models, we ran lots of simulations. One of the first thing that came out was that this mice model, the one I just showed, let's go back. This mice model was the best model when it came to fitting the data we had for consumption. So we have data about how many cigarettes people are having per day on average for different educational groups and demographic groups before and after a given price increase, a tax increase. So we have data on that. And the model that had this component in it, this experimentally validated one, was the best in telling us, in fitting the numbers for consumption. However, it didn't have a framework for allowing people to quit and relapse or to initiate cigarettes, and that's a very big component of sort of the smoking model. And so the best overall model is the model that it's the perceptual control theory. I'll show it in a moment, but it basically has that that perception that the more my friends smoke, the less I feel I'm a smoker. And so this is the perceptual control theory model has been published on in some papers, and so it's the one that came out for us, and so we will be using this model to actually generate policy outputs. Yeah, that's the one. Okay, so this is the perceptual control theory model, and I can just maybe go through it really briefly as sort of an example of a type of feedback-rich behavioral model we might want to consider. You can see that it's done with the system dynamics package, which is another really important reason why we use AnyLogic, because it's arbitrary to the method, it's agnostic to the method. So in the bottom right, you can see that there's this stock. Maybe you can't see it. It's called addiction action, and the idea is that people are going to change their action to bring their perception in line with some intent value. So there's this reference signal, there's a perceived action, and then in the middle there's an error term. And if the difference between those numbers is positive, you're going to increase your action. If it's negative, you're going to decrease your action. But importantly, your perceived action, in this case, the action corresponds to the smoking rate. So your perceived smoking rate is going to be a mix of your actual smoking rate plus external signals. So in this case, there's external signals, which is coming from your social network and from the people that are in your physical environment. There's parameters here that we can tune to figure out how much of those to consider, but that's the idea, that you have these external signals. And then on top of that, there's this other loop which controls this intent. So it's this intent loop. And so again, it uses your perceived action, and then what it does is it controls a reference signal for the bottom loop. So this is based on theory work that was done by an engineer, William Powers, in the 70s and 80s, and it's been looked at since then as well. And I have 3 minutes left. There's this other model that I can get into. This is the mouse model. There's these different levels where, again, it's sort of a feedback-rich system dynamics model where you've got levels of what they've called toxicity or habit or hedonistic memory. There's a whole paper on it. And this is the one that fit really well for the consumption patterns, but it didn't fit well for the quitting and initiation patterns because we had to put our own sort of extras into it that weren't externally validated. So it would be really helpful if we can sort of go into a lab setting and test some of these things, even in animals, because then we can show that they work really well in agent-based models for humans. So why AnyLogic? Method agnostic, agent-based system dynamics. We actually had to convert the system dynamics into sort of numerical solutions because system dynamics within agents turns out to be quite slow. And the visual coding is really key. You know, I'm the modeler on the team, and the people I'm working with are domain experts, so it's really vital that I can communicate the assumptions that they're putting in the model without showing them code, and that's a really key piece. And then the fact that we're using a mature object-oriented language like Java was really key for us. That's all I got. Thank you.
Hi. So in your talk, you spoke about noisy or missing data. So how do you address that issue?
So it's a good question. How do we address the issue of noisy and missing data? The problem is that the models that we're building depend on a lot of latent characteristics, things that we can't observe. So I don't know if anyone's familiar with the literature, but there's a behavioral framework called the theory of planned behavior. And so they do statistical tests, they ask questions, and they try to look at outputs and inputs. And really it depends on this level of perception. So we're getting data about people's sort of perception, but it's not a straightforward thing to convert that into an agent-based model because it's a statistical model. So we know that there's things taking place that we're not measuring. And so the goal, I think, is really the scoping question, is we want to make sure that we're not including so much in the model that some latent characteristics we don't think are there are really driving the system. But again, this is where the model is about insight and not prediction. So if the model is generating types of behavior, drinking behavior, congregation behavior, if people are drinking way too much or smoking way too much or not enough or something, then we know there's something wrong in the model, and then we can begin to challenge those assumptions. So the goal of this is to basically take all the assumptions that we think are true and try to put them in the model in a principled way and test those assumptions. Yeah.
Hi, it's a nice presentation. I have a question. In your experience, how many loops or intended actions, I mean the inputs of the main model, how many process is the best recommendation to standardize the model, the results? I mean, the loops that you present.
The feedback loops?
Yes. Is there any relation in the quantity of these loops with the mean results of the model?
Do you mean like specifically the loops within the framework or just general feedback loops?
General feedback.
Oh, I don't know. I mean, there's a lot of literature in the system dynamics community about looking at the behavior of loops and at combinations of those loops to look at So for example, if you have a reinforcing feedback loop, then what you're going to get is a trend that shoots your number up into infinity or tanks it towards 0 really quickly. But if you have a reinforcing feedback loop with a balancing feedback loop, then you get this sort of goal-seeking behavior. So a lot of the times in the system dynamics community, what you start with is like general time series shapes of your data, and then you try to infer things about the underlying causal loops that might be causing that, and then you can test that with models. So there is a rich literature in the system dynamics community about how to judge that, and it's not really just about the number of loops, but their orientation with each other. Yeah.
Oh, hi. Yeah, very interesting, very complex, and, well, congratulations.
Thank you.
Well, my questions are, one of them is about the framework. You mentioned the framework a few times for discrete choice behavior, for feedback loops, for validation, and for perception control theory. Let's say all of those things. There is a question of what makes you decide to place all those areas of the behavior or the model itself into this, what you call framework? Or what is the, you said it's an agent within agents.
Yeah, so the idea, the reason why we were using this framework agent is just so that we can, because a causal loop diagram, a complex systems model, if you change one little thing, you'll often get changes that you didn't expect. So what we wanted to do was be able to have a single model file that contained within it many different, switchable assumptions about human behavior. And so the best way that we could figure out to do that was to use essentially a Java interface and to specify this interface object, and so that the agent, this sort of framework agent, gets turned on or off at the beginning of the model. So an agent might have 10 different framework agents, but only one of them is ever being used. And so when the model runs, we have a parameter that just tells you which framework to use. And the only reason why we put the framework in there is so that we could really quickly, it's not part of our experimental setup, so we can, in a parameter variation experiment, we just switch that framework, and we can just set the computer to run, come back a week later or whatever, and we have the different outputs for which behavior framework was used. So it was more like an implementation tool. You could do this without it. You just have to have copies of your model for all the different behavioral frameworks, and when you make a change in the model, you have to propagate it through all your models to keep it the same, and that's not going to work. So to protect ourselves from that, we did this.
The other question I have is regarding the, what made you decide the use of system dynamics instead of the agents themselves as modeling?
So for the behavioral frameworks?
Yeah, in general, because you said that you had to move, and actually the main diagram that you show is about system dynamics as far as I can see.
Do you mean like the behavioral framework?
That one, yeah.
Yeah, so system dynamics, I think one of the amazing reasons why AnyLogic needs more and more attention is because it really allows us to use multiple methods. And I don't know, in my experience modeling, I've been using AnyLogic. I did my PhD with AnyLogic. I've been using it for 5 or 6 years now. I've gone to a few conferences. I sometimes struggle in seeing not a lot of communication between the agent-based and the system dynamics community. System dynamics is a really powerful technique, and one of the most important things I find about system dynamics is that it enables you to visually represent complex qualitative knowledge, right? And so causal loop diagrams map really easily to a system dynamics setup, and causal loop diagrams we use all the time for mapping out kind of how people make decisions. So it's a really useful tool for visually representing what you're trying to understand. And when you're designing something with domain experts who know the knowledge, a visual tool is really powerful. So in some ways it's better than what agent-based modeling is able to accomplish so far, although there's a lot of room.
This perceptual control implemented in system dynamics, are they embedded in every agent, or they are generic?
Yeah, it's embedded in every single agent. There were some technical issues with that, that we actually had to replace the system dynamics models with numerical solutions to the system dynamics models to make it run effectively. But for trial purposes, we were able to do this, yeah.
Now, in which part of all these parts that I didn't hear you mentioning in particular is the role of emotions in the decision system?
Right, so we looked at a whole bunch of behavioral frameworks that some include emotions, some don't include emotions. I think it would be great to basically these don't include emotions explicitly. So I think it would be great. The difficulty is in learning how to quantify a qualitative theory. So there's a lot of theories that include emotions, but they're sort of qualitative. And so our goal was we wanted to kind of grab the lowest hanging fruit and to run those because, we only have so much time. But this technique would be able to be used to help quantify those qualitative models in the future for different research goals. But the client had different desires, so we worked with that.
Yeah, great.
Thank you so much.
The lower end fruit, I think, is good. Thanks.
Thank you so much.
Thanks.
Thanks.